everyone and welcome. Today we're going to be discussing chemical equilibrium. By chemical equilibrium, I'm meaning chemical reactions that are in balance with one another. So chemical would be our various different chemical reactions, and equilibrium is speaking about balance. Now, if you've got reactions in balance with balance one another, the forward and the reverse reaction are taking place at the same time, and they are taking place at the same speed. So overall, you won't see any effect, but both reactions are taking place. Let's consider two conditions for this to occur. Well, our conditions must be that both reactions occur, so that you can actually have both the forward and the reverse reaction. Now, only certain chemical reactions are both forward and reverse reactions taking place simultaneously. So that is indicated by our double arrow. It's shown like that. And it's at the top arrow forward, bottom arrow reverse. The second condition is that you must have a closed container. What do I mean by a closed container? Well, we can't have any of the stuff escaping into the atmosphere. It can't be escaping out. We are trying to make sure that this whole thing is an isolated environment, so that both the forward and the reverse reactions do take place simultaneously and at the same speed. Let's get going in terms of seeing what you need to know about chemical equilibrium. Here's a bit of a checklist for you. Make sure that you can explain the concept of what chemical equilibrium is. So that is a definition of chemical equilibrium, and maybe you might be asked about what conditions a reaction could be in equilibrium, and specifically if this scenario that you might be given in a question is in equilibrium. Then we could be asked to draw and interpret graphs. Now, graphs are vitally important for a system in a chemical equilibrium, and we can read off lots of information from a graph. Then also recall the factors that change the position of chemical equilibrium. And so you need to be able to list those various reactions, maybe temperature or pressure, all affects the chemical equilibrium itself. And so we would need to investigate each of those, and you need to be able to discuss each of the various conditions, or factors, I should say, that affect chemical equilibrium. Then there's a principle or a law that we can apply. It's called Chatellier's principle, and it's a very important law. We're going to get to it in a few minutes. The other thing you need to do is be able to calculate a value for Kc, the equilibrium constant. And we'll look at lots of Kc calculations in today's lesson. So stay tuned. Let's dive straight into the questions. Question 1. We get given a reaction, the industrial preparation of hydrogen gas, and I'm thinking hydrogen gas, H2, diatomic gas, is represented by the equation as follows. We have methane with water, forms carbon monoxide and hydrogen gas. And the reverse is true as well. Hydrogen gas and carbon monoxide can form water and methane. And so it's both a forward and a reverse reaction. They tell us the reaction reaches equilibrium at 1,000 degrees Celsius. That's a temperature bit that we need to note in a closed container. So by closed, it is an isolated system, and nothing can escape. So you can have a forward, the products becoming reactants again. Let's have a look at what the question says. This question says, state Le Chatelier's principle. So they're going to be looking at possible changes, and we need to be able to predict what would happen when we look at those changes, or factors that affect equilibrium. Le Chatelier's principle is a very important law or principle you need to learn, and I have it on the board here in a moment. This is a definition you need to go and make sure you understand and learn. When the conditions affecting an equilibrium are changed, so something is changing, the equilibrium position shifts in such a way to oppose the change or cancel out that change. So you have a system that is already in equilibrium. We suddenly do something to change it. We change the various factors surrounding that equilibrium position, and the whole system will react to oppose that change, to cancel out that change, to negate that change. So the three ideas is that you've got an equilibrium already established, we do something to change it, and the whole system, the forward and reverse reactions are shifted to favor one or the other that would cancel out that change. You need to go and make sure in your textbook that you are well prepared for this, stating this principle. 3 marks, the fact that it was in equilibrium, we've done something to change it, and the system responds to cancel or oppose that change that has been imposed on it. Question number 2. Again, we have the same chemical reaction and a sub-question of that. How will an increase in pressure, now pressure is one of the things that affect chemical equilibrium, at a specific temperature by decreasing the volume. And you know, if you if you decrease the volume of a container, the pressure inside will build up. So we're increasing pressure by decreasing the volume. How will that affect the yield of hydrogen? Now, the yield of hydrogen, we need to go and look at our chemical equation and say, where is hydrogen? Hydrogen is over here, which is one of the products, if we're reading this as a forward reaction. Okay? How will an increase in pressure affect the yield of hydrogen? Yield means the production of hydrogen gas. Write down only whether it increases, decreases, or has no effect, and then give an explanation. So you're going to get a mark for making a simple, will it increase, decrease, or stay the same? Explain your answer is the next point we need to look at. Well, have a quick look at this reaction. I want to consider the number of moles in a very similar way as if we're all a group of people in a lift going up a couple of stories in a tall building. When would the pressure be high? Well, when there's lots of particles or lots of people in this lift and we all cram together. That would make a significantly high pressure, and you would feel everyone else pressing up against you. Whereas if there were only a few people in the lift, the pressure would be much less. So how is this system going to change? Well, in the same way as I'm saying people in the lift, we can count the number of molecules or moles of gas, the number of moles of gas here. And how I would do that is look at the numbers in front. Now, there are no numbers in front of here, but we understand that those values are 1. So 1 mole of methane gas and 1 mole of water or water vapor is going to give me an overall 2 moles of gas on the left-hand side of this reaction. Have a look at the other side. Well, again, 1 mole of carbon monoxide, but 3 moles of hydrogen gas. Overall, this right-hand side of the reaction will have 4 moles of gas. So comparing those two, if I've increased the pressure, the system will react to decrease or lower that pressure, and it will do so by favoring the reverse reaction. So it will favor making 2 moles of gas. Let's have a look and check that we have the correct answer. Well, Notice here, we're always having to answer our question. The question was the yield of hydrogen. How will it affect the yield of hydrogen? It would decrease the yield of hydrogen because I'm favoring not the forward, but the reverse reaction. So overall, the reaction would be favored in the reverse. So hydrogen production is going to decrease or become lower. Let's go through it. Hydrogen production would decrease because as the pressure is increased, the reverse reaction is favored. We've mentioned that. Why? Because the reaction that produces the smaller volume or amount of gas must be favored. Again, you would also get marks if you discussed the 4 moles or the 4 volumes of gas producing 2 moles or 2 volumes of gas for the reverse reaction. Let's move straight along. Right. We now have another sub-question to this question for this reaction. Give 2 reasons why high temperatures is important, are used for this reaction. So we're looking at possible reasons why we would want this entire reaction to take place under extremely high temperatures. Well, this links to 2 chapters. Firstly, it links to chemical equilibrium. But before that, I'd like us to link into the idea of rates of reactions. And you've probably studied a chapter on rates of reactions and know that a reaction will take place faster if there are higher temperatures. So let's have a quick look through here. The solution, products would form at a faster rate, and the faster rate is going to deal with the higher temperature, because increased temperature is going to give me an increased rate of the reaction. Now that is because particles move faster, they have greater kinetic energy at higher temperatures. So they're moving faster, they will collide more frequently, there will be more effective collisions, and so the rate of the reaction will be that much quicker. Then the second point, so that was point number 1. The second point is going to be linked into chemical equilibrium, where both the forward and reverse reaction can take place. Now, the rates of chemical reactions will affect both the forward and reverse reactions. But specifically when we look at equilibrium, we need to consider if this is an exothermic or an endothermic reaction. And when I consider this reaction, you get a piece of information on the side here, which is very important. That little bit of information is telling me whether this reaction is endothermic or exothermic. It is saying that delta H is greater than 0, which means it is a positive value. If it's a positive value, if it's greater than 0, that means that the forward reaction overall is going to be endothermic. Endothermic means it takes in energy. It requires energy, and usually in the form of heat. So here, if we have increased temperatures, it's going to favor the reaction that uses up that excess that heat, and it would favor the endothermic reaction, which I know is forward reaction. So that's our second point over here. A higher yield of products would take place if I had higher temperature, and the products meaning carbon monoxide and hydrogen, because the forward reaction is endothermic. And I got that answer by looking at the delta H. So that's the end of that question. We're going to take a quick break now, and when we come back, we're going to tackle some KC calculations. Welcome back, everyone. We're going to now start to tackle some KC calculations, and students do often struggle with KC calculations, so pay close attention. This is a follow-on from the first part of question 1, and they say, study the reversible reaction By reversible, we mean it takes place in both directions, so both the forward and the reverse reaction, represented by the balanced equation below. Now, I'm going to underline this word balanced because your reaction needs to be balanced in order for us to work with the following calculation. So we have hydrogen gas, carbon dioxide, water, and carbon monoxide. And they tell us quite a lot of very important information in the coming paragraph. Initially, at the start, X moles of hydrogen gas is mixed, so we don't know what that value is. It's X moles of hydrogen gas is mixed with 0.3 moles of carbon dioxide. And I'm just going to jot these figures down. 0.3 moles of carbon dioxide is mixed in a sealed 10 cubic decimeter container. Now that 10 cubic decimeter is vitally important. It is a volume of 10 dm cubed. When equilibrium is reached at a certain temperature, it is found that 0.4 moles of water is present. Then they tell us something about the equilibrium constant. The equilibrium constant, the Kc value for this reaction at this specific temperature is equal to 4. Now the Kc value is a ratio of products and over reactants, but specifically the concentration of products over the concentration of reactants, taking into account their stoichiometric ratios. Let's have a look at what the question's asking us to do. There's my equation. Calculate the initial number of moles of hydrogen gas. So initial means the start, and I'm looking at how much X, how many moles of X did I put into this reaction, or this container. Calculate the initial number of moles of hydrogen gas, X, that was in the container. Now the best way to do this is to set up a table so that we can analyze each of the reactants and the products in a systematic way. Now, I want to start always by looking at a balanced chemical reaction. And let's draw up this table. Now, I've got it on the screen already, but I want us to talk through it in quite a bit of detail. So please do follow closely. This table has the 4 columns for my 4 substances in this reaction. I have an initial quantity given in moles. I then have what's changed. I have the quantity at equilibrium. It's either left over or produced when we get to this equilibrium point. And then I have a concentration I'm going to work out. So let's go back and make sure that we've got all our details. I'm going to spend a moment and just write down my reaction. H2 plus CO2, forward and reverse reaction, H2O plus carbon monoxide. Okay? We were told that we had X as our quantity. It's an unknown value. That's what I'm going to have to work out. We were told that 0.3 moles of this carbon dioxide was put into this sealed container. So an unknown quantity, that's my question mark, that's what I'm trying to find, plus 0.3 moles of carbon dioxide with nothing else. So I can put 0 and 0 for those products. They haven't been formed yet. Now I need to work out, put any other information on this table so that I can work out, using ratios, how to find what the change has been. They tell us in the question, originally, let's go back to it, that it is found that 0.2 moles of water was present when we got to equilibrium. Okay, that's critical. So let's go and put that in on our table. Sliding down. at my table again. This is the 0.2 this is the 0.2 I'm now putting into the table. That's a new value, okay? A value that I was given. This is where it starts to get interesting. We are simply dealing with ratios, okay? Now, if I come to the top here, I want to write in the ratios. They were given to me. Remember I said this has to be a balanced chemical equation. So have a look, balanced chemical equation. I've just copied it down so that we've got it. 1, 1, 1, 1. Now that's quite a straightforward, simple one. Those ones are not written in because they're understood values. Just like you wouldn't write 1x. You would just understand it as, in maths, as being x. We don't need to write the 1 because it's understood. In the same way, those 1 values are understood. So our ratio here is going to be, if I have 0.2 moles of water, I must also have 0.2 moles of carbon monoxide, because they're in a 1:1 ratio. So 0.2 moles has been formed. I was told that. We know that if 0.2 moles of water is formed, the same amount, because of the 1:1 ratio, of carbon monoxide is formed. Working back, I would say the same amount, 0.2 moles, had to be used up from the reactants in order to get there. So we have the 0.2 moles on this side. And then similarly, there must have been 0.2 moles of hydrogen that has been used up. Now, notice for the reactants, which are these ones, the 0.2 is a negative value. That negative value is very important. It's telling us that it's been used up, whereas the positive on this side means it's been produced. Okay? The negative on this side, I'm going to jot it in here, means it's been used up. Okay? That I determined from my mole ratio. And in my memo here, we've even got the word ratio with a tick, because that's where you're going to come with marks. That's your working out, right? Now we're looking at the quantity that is now measured at equilibrium. So obviously I was told 0.2 moles was at equilibrium for the water. Similarly, there must be 0.2 moles of carbon monoxide. But remember I said these bits on the left-hand side have been used up because they're reactants. So I have to work out what did I have minus what was used up. I'm going to be left off with the 0.3 minus 0.2. So left over, if you like, there is only 0.1 moles of carbon dioxide. What about the hydrogen? Well, I don't know what that original value was. I'm trying to work it out. So let's write x minus the 0.2 that I know must have been used up in terms of my 1:1, my ratio, my mole ratio. So this is my quantity at equilibrium, and I'm going to write there left over, if you will let me. The equilibrium concentration. Now this concentration is going to be critically important, because remember we got given information about the Kc value, and that Kc value is going to come into play in a moment. So the equilibrium concentration is we're working out from the number of moles, we're now going to a concentration. And the formula for working that out is concentration is equal to number of moles divided by volume. Just have a quick look at the units for concentration. It is moles per decimeter cubed. Or another way of writing it, moles dot dm to the -3. This decimeter cubed is very important. Remember I said to you we had information in our first initial question that said the sealed container was 10 cubic decimeters. So I'm going to take that value and use it over here sorry, my question keeps going away. I'm going to use it as I work out what the concentration would be. Let's start on this side. I'm dividing the 0.2 moles by 10. So, there we are. I'm dividing that 0.2 moles by 10, and we'll notice the decimal point has moved one place. Again, 0.2 moles divided by 10, 0.1 moles divided by 10. Now I come across here, and this is what I'm going to be using to work out the value of x. So now we're going to use the value for Kc that we were given in the question to work out the value of x. The Kc value is a very important value. It's a ratio of products over reactants. But not just products over reactants, we are going to be dealing with the concentration of the products and the concentration of the reactants. So this value will tell us how much substance is coming out. A high Kc value is an indication to you that you've got lots and lots of products coming through at this point in the equilibrium. We specifically also look at the numbers in a balanced chemical reaction. And those values, those numbers, the big numbers in front of the chemical formulae, will tell me specifically what exponents or powers need to be up here. So the stoichiometric, the balancing numbers become my exponents. Now I have balancing numbers of 1 and 1 and 1. So our exponents are not going to come into play just yet, but let's go back and make sure we've got the concentrations. So this is our concentration for my hydrogen gas, the concentration for carbon dioxide, the concentration for water, and the concentration for carbon monoxide. They get put into my Kc value, and I'm now looking at this over here. The Kc value is the concentration of the products. So I've got carbon monoxide and water at the top, divided by the concentration of the reactants. So hydrogen and carbon dioxide at the bottom. Substituting those values, I have the values from my table being plugged in. But we were told in the question that all of this was equal to 4. The Kc value was equal to 4. So I can rearrange and solve this equation, and we can find the unknown x is what I'm looking for. And it works down to x being equal to 0.3. You might need to go back and check that you can do the math and taking the denominator on the side across and working it out. So we get x being 0.3 moles of hydrogen gas, which was what my original question asked me to find. Let's move on and tackle another Kc problem. The next question, 1.2.2. The reaction is now carried out at a much higher temperature. Much higher temperature. It is found that Kc decreases. That's critical. Is this reaction exothermic or endothermic? So they're not telling us what delta H is. We need to work out whether this is endothermic or exothermic. We have got information, but I want to focus firstly on the Kc decreasing. The Kc value, remember, is the value of a ratio of the concentration of products divided by the concentration of reactants. If this value decreases, what does that tell you immediately? Well, it tells me that products are becoming less. There are less products at this higher temperature. And I'm just jotting that down for myself, higher temperature. Is this reaction an exothermic or an endothermic reaction? Exothermic, you're thinking it gives off heat. Endothermic, you're thinking it takes up heat. And going back to Le Chatelier's principle, if the system which was in equilibrium has something changed to it, has some kind of stress added to it, for example, increasing the temperature, the system will react to cancel out or to oppose or to negate that effect. So have a look at what we've got. We've increased the temperature. The system has favored which reaction, the forward or the reverse? Well, we know that suddenly our products have become less. That means our reactants must have become more. So it's favoring the reverse reaction at this increased temperature, right? Have a look down at the solution. They say to me that the reaction is exothermic. Now, by answering that, they're actually saying that the forward reaction is exothermic. Why? These are my reasons. Because I had a decrease in Kc, it means that I had lower product formation or product concentration, less products or higher reactants. Obviously, that's the converse. More reactants. The reverse reaction is favored. That tells me that the forward reaction must be exothermic, because if the reverse reaction is favored, the reverse reaction would be the reaction that uses up that excess heat. Because I've increased the temperature, the whole system will shift to use up that extra heat. Let's move to the next question. Here, completely new question, but a Kc question nonetheless. Consider the following equilibrium reaction. This is quite a classic reaction, the Harbour process. We have lots of information given to us as well. 9 moles of nitrogen gas and 15 moles of hydrogen gas are pumped into a 500 cubic centimeter container. Immediately when I see that, I know I must convert to cubic decimeters. I don't want it in cubic centimeters, I want it in cubic decimeters. That is 0.5, because I'm dividing by 1,000 in this cubic form. Container at room temperature. The temperature is now raised to this, resulting in 8 moles of ammonia being present at equilibrium. Calculate this new value of Kc. Okay, so I've got quite a bit of information, and again, I find it easiest to work in a table. Let's have a look at how I would set out my solution. Well, once again, it's always helpful to have written the chemical reaction. And now I'm going to write in all of the information that is given to me. So nitrogen, I was told, and I'm going to slide up here quickly, I was told there were 9 moles of nitrogen gas present. So 9 moles gets fitted in. For the hydrogen gas, I was told 15 moles of hydrogen gas were pumped into this container, and there was no ammonia, so there's a 0 there. Let's now consider what else I was given. The volume, we'll come to the volume in a moment. Let's go across to this 8 moles. The 8 moles of ammonia were present at equilibrium. So I come across to my table and I fit in this 8 moles of ammonia. Now I need to work back, and remember I said to you this has to be a balanced chemical reaction. So I'm going to take this reaction and write it down over here. Let's change our pen color. It is N2 plus H2 forward and reverse reaction forming NH3. Let's go and fit in the balancing numbers 1, 3, and 2. Okay, coming down again, so I've got that in front of me. If 8 moles of ammonia NH3 is present, how much nitrogen is present? Well, go back and look at these balancing numbers. That's a 1, understood 1, and 2. So I will have twice as much ammonia as I will have nitrogen. So I'm going to fit in half of 8 will give me 4. The way to do this is to divide by whatever number's in the front there. Okay, so now we've got a 2:3 ratio. This is going to be a little bit more challenging, but divide the 8 by 2, it's going to be 4, and then multiply by 3. So divide by the 4 by 8, the 8 by 2 from here, and then multiply it by 3. And so you will notice 8 divided by 2 is 4, multiplied by 3 gets me the 12. And that's why I come to this number 12 over here. That is the number of moles that is either used up, whether it's reactants, or that is formed when I get to be in this whole process. The next idea is we're going to say, what is happening at equilibrium? Well, what have I got at equilibrium? Again, I'm starting with the ammonia. I have 8 moles, the number taken straight down. Let's just erase some of this. I will now have only 3 moles of hydrogen left. How did I get there? Well, I said I had 15, I've used 12, so I've only got the 3 left. Similarly, we'll do the same thing for nitrogen. I had 9 pumped into the original container. I used up 4 moles, and I worked that out according to the mole ratio. So I've only got 5 left. Now the next idea is we need to calculate the concentration. So I have 5, but what is the concentration? This is number of moles, but this is a concentration which is measured in moles divided by the cubic decimeters, divided by the volume that is in my container. Going right back to the top, do you recall that we got given this number, 500 cubic centimeters? That number needs to be in cubic decimeters, because if you look here, we've got the concentration units will tell me it's measured in cubic decimeters. So we'll take that value, whatever it was, and divide it by half a cubic decimeter. So I'll start at the end where I've got a bit more space, and I've got my concentration number of moles divided by volume is equal to 8 from this top value here, divided by 0.5 was my volume, dm cubed, half a cubic decimeter, and it was 8 moles. And that's going to take me to 16, which is what I've got in a table with a little tick there. 16, 3 divided by 0.5 is going to be 6, and 5 divided by 0.5 will give me 10. So now I have concentrations for each of these substances. Again, I'm going to plug them into my Kc formula, and this formula is always going to be the concentration of products divided by reactants. Concentration. Okay. Concentration of ammonia, which was my product, divided by the concentration of nitrogen and hydrogen. Now hold on. what have we got with these powers, these exponents? Those are coming again from my balanced equation. We have ammonia with its mole ratio. We have nitrogen with a little 1 up at the top there. Doesn't need to be written because anything to the 1 is fine. And the 3 for hydrogen. Those are vitally important. So you would need to take your calculator, 16 squared. I would recommend that you actually just write down the value and then work out the division a little bit later, but it depends on how good your calculator skills are. So 16 to the power of 2, 10, also all these values are substituted directly from my concentrations in the table. And I come up with a final answer for the Kc value, which is what I was being asked to calculate. Now this question is worth about 6 marks. Very, very important question. From here we're going to take a break and we'll pick up again looking at some graphs and a few more questions on chemical equilibrium. Welcome back. We're about to tackle the last question on chemical equilibrium, specifically dealing with some graphs and how we can interpret and look at graphs and in chemical equilibrium. Consider the following reaction. Sulfur dioxide, SO2, and oxygen react to form sulfur trioxide, SO3. The graph shows the amount of SO3. The amount of SO3 was plotted against time as shown below. Now, we are asked 3.1. How does the rate of the forward reaction compare to the rate of the reverse reaction during the following intervals? Write only greater than, equal to, or less than. And so our first interval they're asking us is between O to A. Now, going back to our graph, O to A is this first interval, and what you should notice is that in this first interval, SO3 is increasing all the time. So the rate of the forward reaction must be greater than the rate of the reverse reaction. The next interval they're asking us to consider is the interval from B to C. So again, going back to my graph, B to C is this third interval over here. Well, the amount of SO3 is decreasing. So I'm writing there decreasing SO3. And so you would notice, well, the rate of the reverse reaction must be increasing or favored. And so we can say that if I go back to my question specifically, how does the rate of the forward reaction compare? It must be less than at B to C, less than the rate of the reverse reaction. And the last one from D to E, going back to the graph, D to E is this final one. Now this horizontal line is telling me that there is, and if I can trace it all the way back, with a ruler of course, there is no change. So, no change. So SO3 is remaining constant. The rate of the forward reaction and reverse reaction are equal to one another. And so answers simply there would be greater than, less than, and equal to in that order. Going along to question 3.2. This is going to be another Kc calculation. Initially, or at the start, 0.8 moles of SO2 and X moles of oxygen are placed in a 2 cubic decimeter, sorry, I've gone over that a little bit, 2 cubic decimeter empty container and are sealed at a specific temperature. Once again, I want you to note the volume of this thing is 2 cubic decimeters, very important, and sealed at a specific temperature. At equilibrium, we come out with 6 moles of sulfur trioxide are present in the container. If the Kc value of the above equilibrium is 9, calculate what was X, as in that is the initial amount of oxygen that was placed in the container. Again, lots of information. I think it's wise to put this in a table as we answer these questions. So, once more, I've got an initial volume and I'm going to put in all the information into my table. So, have a look. We had 8 moles of sulfur dioxide, 8 moles there from the information. X moles of oxygen, and it was an empty container, so 0 moles of SO3. The number of moles either used or formed. Well, I'm going to have to work this out, but let's figure out where do we put the 6 moles are formed at equilibrium. So my next row on my table is the number of moles that are formed. 6 moles of SO3 was formed. I go back to my equation and I can write this equation. I'm going to write it again just a bit lower down, so that I can work with it. 2SO2 plus O2 forms 2SO3. Okay, moving right along. Let's have a look here. Well, this is a 2:1 ratio. So 2:1, there's an understood 1 there. So notice if I've formed 6 moles of SO3, I must have used up 3 moles of oxygen in that process. And then working back, it's a 2:2 ratio, so 6, they must have used up 6 moles of sulfur dioxide in the process as well. So how much do I have left? This is left over, if you like. Well, I had 8, and I've used 6, I've only got 2 left. I had X, I've used 3, so it's X minus 3. I had 0, and I've formed 6, so that's a positive value because it's been formed or produced. Again, I go on, when I work with the concentrations, I need to take into account the volume of this container. Well, the volume, remember, was 2 dm cubed. I have 2, so it's 2 divided by 2. 2 moles divided by 2 decimeters cubed, giving me 1. That X minus 3 divided by 2, and then 6 divided by 2, giving me the 3. Now take those values and plug them into our KC calculation. Concentration of products divided by concentration of reactants. Notice here I have these exponents coming from my balanced equation. Okay, so plugging into the calculator, 3 squared, all the others as is. The whole thing I was told is equal to 9. So I can work that out and solve for X. Taking this to the other side and solving for X. Let's tackle some more questions. We get asked a little bit about the graph, so I'm going to have to jump back to the graph in a few moments. But they're saying to me that if the changes on the graph from B to D are due to changes in the temperature, then at which point B, C, or D will the temperature be the lowest? So I'm looking for where would I find the lowest temperature if I looked at that graph. And I'm going to jump back 2 slides to my graph. 3 slides to my graph. And here we're looking at this period between B to D. There are lots of changes taking place, and if those changes were due to temperature, what would they be? Well, where was the lowest temperature? Now, have a look at this equation, and you'll notice a piece of information on the side here that tells us about delta H, and delta H is here less than 0. So I always write in that is a negative value. That's my little acronym for negative. That negative value says to me that this forward reaction is exothermic. Okay? So looking at the graph, the temperature here must be the lowest because a decrease, and I'm going to go across to my explanation here. Let's jump a few slides. We get the next questions asking us for an explanation. The forward reaction is exothermic. In an exothermic reaction is favored specifically when we have colder temperatures. So the exothermic reaction would be happening when I have the lowest temperature at point B. And the answer for the previous one here they asked us was solution B. Let's go along to the next question. 3.5. At which point B, C, or D will the Kc value be the greatest? Now, if we're considering Kc value, I'm always considering products over reactants concentration. So, when will the products be the most? Because that would give me the greatest Kc value. Heading back to my graph, right at the very beginning, I have the highest products at point B. Compare point B, point C, point D. Point B will be the greatest. The next question asks me to explain it, and I think we've already done that. So that was the next one. 3.5. Give an explanation. Well, our explanation would be that we have more products at point B and therefore a larger Kc value. The last two. 3.7. If the changes on the graph are not due to temperature but due to pressure, at which point B, C, or D will the pressure be the lowest? Now, I want to take you back to consider the number of moles of each of these things. So have a look here. How many moles do I have as reactants? I have 2 moles plus 1 mole, giving me a total of 3 moles on the left-hand side. And similarly, well, we don't have anything to add, just simply 2 moles. So at which point will the pressure be the lowest? Let's go back and have a look at the graph. You always have to analyze your graph as you consider these. Okay. When would the pressure be the lowest? Well, the lowest pressure would be at point C. And let's have a look at that. The lowest pressure is going to be found, and I'm jumping, sorry, excuse the fact that I'm jumping a lot, when we would want to have, and I just want the words in front of you, a low pressure would favor the reverse reaction. Notice again, and I'll just jot these down for you, it was 2 on the right-hand side, 2 moles on the right-hand side, but 3 moles on the left-hand side. So the low pressure would favor the reverse reaction, and the lowest pressure would stimulate more gas molecules being produced. So that would happen on the reactant side, and we can see that at point C where reactants are being favored. And that's going to be it for today. We're finishing off the Kc values and looking at chemical equilibrium. I hope that's helped you and that your matric exams will go brilliantly. Thanks so much.